My name is Michael Downey, and today we will be focusing on exploring quotients of a polynomial functions pertaining to the rational functions, equalities, and inequalities unit, also known as Unit 5. The question we'll be doing today is number 3, A, B, and C on page 262 in the Nelson Advanced Functions textbook. Number 3 is, write the equation for which the properties are given. 3a, a whole at x equals 1. So knowing this, a rational function f of x is equal to p of x over q of x has a whole x equals a if p of a over q of a equals 0 over 0. This occurs when p of x and q of x contain common factor of x minus a. An example of this would be something like x minus 1, x plus 4, all over x minus 1. Now in this instance, when we plug in the 1 in for the x's, these two will then cancel each other out, creating a whole at 1. And if we were to draw a graph, our graph would look something similar to and remember the arrows. And that is 3a. We then move on to 3b. 3b has a vertical asymptote anywhere on the graph and a horizontal asymptote along the x-axis. Now a lot of people are saying, what the heck's a vertical and horizontal asymptote? Well, a rational function f of x equals p of x over q of x has a vertical asymptote at x equals a if p of a over q of a equals p of a over 0. So, if the number you plug in for x and that makes 0 on the denominator, then you know that's going to make a vertical asymptote at that number, because it cannot equal that, or as Wills would say, the world would end. For a horizontal asymptote, a rational function f of x equals p of x over q of x has a horizontal asymptote only when the degree of p of x is less than or equal to the degree of q of x. But you might be asking, well, what happens if the numerator has a bigger degree than the denominator? Then we'd have something such as an oblique asymptote, which is a dotted line through the middle and the graph drawn around it. Then you might ask, well, what if you have both of the same degree? What you do there is you take the leading coefficients for both, and then you divide them both, and then the number you get will be your horizontal asymptote. So in the example we have there, 2x over x, it's just 2 over 1, so you know the horizontal asymptote would be 2. Now back to our question. An example of this would be x plus 2, x plus 3, all over x squared plus 2, x plus 3. Asymptote anywhere, and in this case it'd be negative 3, as written here. And then we have the horizontal asymptote, as explained earlier, with the lower degree being on top, with the higher degree on the bottom, meaning it would be at 0. So our graph would look something like this. And then last but not least, 3C is a combination of A and B. And what we're looking for there is a hole at x equals -2 and a vertical asymptote at 1. So this pertains to what we said before about what if we had the same coefficients on the top and bottom. You take the leading coefficient. And like the first one about the hole, if you can common factor it out, you know you have a hole in that on that spot. So an example of this would be x plus 2 over x plus 2 by x minus 1. So in this instance, we see the hole at -2, which would be about here. And then we'd also see that we have the vertical asymptote at -1. Making our graph look something like so. And that is questions 3A, B, and C on page 262.